So let's work through these examples. So it says, show that each statement is false by finding a counterexample. So we need to find an example that makes the statement false. So you're going to notice here that number 1 and 2 are repeated. So I'm just going to start with number 2. So all prime numbers are odd. So my counterexample statement would be prime numbers, or let's write all prime numbers are, and then instead of putting that the answer is odd, we're going to say not odd. And then in our mind, when we think of not odd, we need to think of, well, what is an example of something that's not odd? It would have to be even. So let's think of a prime number that's not odd, but even. So let's think of prime numbers. 1 is kind of a weird example. It's not prime. It's kind of in the weird scenario. The only way I can multiply to get 1 is 1 times 1. So there's only one factor there instead of 2. Let's look at the number 2. 2 is prime because how do I multiply to get to 2? 1 times 2. So my only factors are 1 and 2. 3 is prime because I can only multiply 1 times 3, and so my only factors are 1 and 3. But we can stop right here because if we look over here, we're looking for a statement where the prime numbers are not odd, so they're actually even, and I found one right here. So what I'm going to say about this is that my counterexample is 2. 2 is prime, but not odd. So this is the example that proves my original statement to be false. Okay, maybe an example that you guys might understand a little better. All basketball players are tall. So my counterexample statement would say all basketball players. So that's my condition of the statement. So let's highlight that in green. So that's my condition. In this case, my prime numbers were my condition. My conclusion of the statement is odd. My conclusion of the statement here is tall. So what I need to do is all basketball players are, and then use the word not tall. So I had to ask my Alexa at home to help me with this. So if my counterexample here, if you know anything about basketball, would be Muggsy Bogues, and I probably didn't pronounce that right. He was known to be the shortest basketball player. But if you don't know anything about basketball, then this would have been something you would have to look up to see if you can find a basketball player that's not tall. But again, on an assessment, I would ask you something that's more familiar to kind of everybody and not just about one specific topic. So again, the whole point here is that we're looking for a statement where the green part is true, but the red part, the conclusion to the statement, is not true. So we're finding something that's not tall. Now, the other kind of weird thing in this example is you have to be careful because what do we define as tall? So this is kind of a little weird, but it still gets you to the idea of we're looking for a basketball player that's not tall. And so somebody that's not tall is this Muggsy Bogues, and he's known to be the shortest ball player. The height of a triangle always lies inside the triangle. Okay, so my condition part of the statement is that the height of the triangle is what we're referring to. My conclusion of my statement is that it lies inside the triangle, like always lying inside the triangle. That's my conclusion. So my counterexample statement would be the height of the triangle and then instead of saying that it does lie always inside the triangle, we're going to say does not always lie inside the triangle. So what we need to do is draw a triangle where the height of the triangle is not inside the triangle. So if I draw a triangle like this, the height of my triangle is represented by this distance here. And you can see that this red line H sits inside the triangle. So what we need to do is think of an example of a triangle that has the height not being on the inside of the triangle. So, I mean, if I draw a right angle triangle, which is what you're used to from an earlier math course, the height of my triangle actually sits here and it doesn't sit on the inside of my triangle. So this diagram of this right angle triangle that I've drawn would be my counterexample to the given statement. And again, we can put H and we can say the height does not lie on the inside of the triangle. Okay, let's look at our next example. We're going to highlight what is our condition of the statement. The square root of a number, and I should use the highlight instead of the pen. The square root of a number, that's my condition. So we're talking about taking a square root of a number, and then my conclusion is always less than the number. So what I want to try to show is that the square root of the number, the initial part of my sentence still needs to be true. The condition still needs to be true. So the square root of a number, you can use the same wording that's given in the statement. And now instead of writing what the conclusion says, we want to write kind of the opposite of the conclusion. So is not always less than the number. Now, sometimes the challenging part of these examples is not to actually find the counterexample, is to look at the conjecture and actually know what they're actually talking about. So let's decompose these words. The square root is referring to this symbol here that we've talked about in the radical section. So we're going to take the square root of a number. So I'm going to take any number. Let's say I take the number 9, okay? And the answer to this is 3. So the square root of the number is always less than the number. So my 9, square root of 9 was less than 3. So this is a statement that shows my conjecture to be true. I need to find one when I take the square root that gives me an answer that's bigger than the original number, because the not always less would mean that it has to be bigger than the statement that we started with. So let's look at another example. If I do the square root of 16, my answer is 4. The 16 is bigger than the 4, so the 4 is less than the 16, which is showing that my statement is true. Now, you may not know this, but if I take the square root of 1.1, and I'm going to have to grab my calculator here. So if I take the square root of a number like 1.1, I get this to be 1.0488 ... And again, this one is true. So for me to find an example, I have to start being creative and choosing numbers that I may not think to choose. Now, we know I can't take a square root of a negative number, so let's try something even smaller. Let's take the number 0.52, some just random number. If I take the square root of 0.52, my answer is 0.72111 and then a whole bunch of other numbers. But then when I look, my original number is smaller than my answer, and this is actually a counterexample to the statement that's given. So the square root of a number of, let's write my number, which is 0.52, is larger in this example than the number. Okay, so here 0.7211 is larger than the number I started with. So this is actually a statement that I use. This would be my counterexample. Now the nice thing is you only need to find one example that works. So if you happen to find this one example and then you can't get another example, then at least you found one. But you might have an idea of what kind of numbers to choose now. The sum of two numbers is always greater than the larger of the two numbers. So my counterexample statement, well, my condition is that I'm starting with the sum of two numbers. So I'm adding two numbers up. My conclusion to the statement is that it is always greater than the larger of the two numbers. So let's write my counterexample statement. So we're going to leave the green part the same. The sum of two numbers. Now, instead of writing is not always greater, I'm going to just automatically write this as is smaller, so not greater, than the largest of the two numbers. So when you're looking for your counterexample, you kind of have to do the same thing we were doing when we were making the conjectures and look at observations to see what's happening and then try to be clever to find an example that doesn't do what it's saying. So let's take two numbers. 2 plus 7, this is equals 9. 9 is bigger than the largest of the two numbers, which is 7. So this is trying to show that my statement is true. I need to find one that shows that my statement is false. Okay? So we need to find an example where I take two numbers, I add them up, and the result is actually smaller than the numbers that I started with. So maybe let's try 3 plus 1, which is 4. Now, my answer 4 is bigger than my original bigger number, which is 3. So this is also true. So now if you look and I start to take just whole numbers, you're going to notice that this is going to happen. So we got to be a little bit clever. So let me try to be clever by introducing a 0. So if I take 5 plus 0, this is 5. And my answer is not bigger than the original number. It's actually equal. So this would be a good counterexample to my statement. So I'm going to say 5 and 0 are two numbers. The sum of 0 and 5 is 5. So we take the sum of the two numbers. And we're going to say the result is not bigger than the larger of the two numbers. Now in this example, you can see that I wrote is not smaller, or it is smaller, but we can also write that it's equal here because it's not greater than either. So another way to be clever is to start taking negative numbers, and you might see that this result is going to be still a good counterexample to pick. Okay, number 7. When you multiply two whole numbers, now when we talk about whole numbers, we're talking about numbers that start at 0 and then 0, 1, 2, kind of your counting numbers. When I multiply two whole numbers, I want the product, which means when I multiply them, to be greater than either of the two factors. Okay? So, and the factors are referring to the two original whole numbers that you have. So let's write our counterexample statement. When you multiply two whole numbers, their product, now here it says it has to be greater, so now I'm going to use the word is not greater than either of the two factors. Okay, so we need some observations. Let me take two whole numbers, so let's take 5 times 3. Okay, my answer is 15. 15 is greater than 3, and 15 is greater than 5. So this is showing that my conjecture is true. I want to find one that shows that my conjecture is false. So let me try to maybe take 1 times 7. The result is 7. So 7 is greater than 1, but we're going to notice that 7 is not greater than 7. It's actually equal to 7. So this could be an example of my counterexample, because it says here that when you multiply the two numbers, the product has to be greater than either of the two factors, and here it's not greater, it's actually equal. So my counterexample would be the numbers 1 and 7. I multiply them. 1 times 7 is 7. 7 is not bigger than 7. So this would be my example of my counterexample. Okay, let's look at the next one. The sum of a multiple of 3 and a multiple of 6, okay, that's my condition, must be a multiple of 6. So we're going to write my counterexample statement. The sum of a multiple of 3 and a multiple of 6 okay, now instead of saying must be, is not a multiple of 6. Okay, so let's look at some examples. Let's think about multiples of 3. 3, 3, 6, 9, 12, 15. Those are multiples of 3. 6, 12, 18, 24. I'm counting by 6s or multiplying 6 times 1, 6 times 2. These are multiples of 6s. Now they're telling me I need to do the sum of them. So I'm going to take 3 plus 6. I get 9. And then I want to see, is 9 a multiple of 6? So here I actually already found a counterexample. 9 is not a multiple of 6. So that's actually what I'm actually looking for. So this is already my answer here. But let's even take another example. 6 plus 12, this is 18. 18 does happen to be a multiple of 6. So this would be showing that my statement is true. The first example would be showing that my statement is false. So I need a counterexample to the original statement, or I can look at my counterexample statement and try to find one that is not a multiple of 6. So I'm going to say 3 and 6 are my numbers. 3 plus 6 is 9. 9 is not a multiple of 6. Okay, the last example here. Let's look at my conditions of my statement. The sum of digits in any multiple of 9. And the conclusion will add to 9. So let's write my counterexample statement. The sum of digits in any multiple of 9 will not add to 9. So this is what I'm trying to find an example where I'm going to add the digits up in a multiple of 9, and then the answer is going to be not a multiple of 9. So let's write my multiples of 9. So 9 times 1, 9 times 2, 9 times 3, 9 times 4, 9 times 5, and I can keep going if I needed to. I'm going to take the sum of the digits in any of the multiples of 9. So let's take the example 18. My digits are 1 and 8. I do the sum of those digits, which is 1 plus 8, and I get 9. But then I notice that 9 is a multiple of 9. So this one wouldn't work. Let's try another example. 45. The digits are 4 and 5. I take the sum, 4 plus 5, and I get 9, and 9 is a multiple of 9. So now I have to be a little bit clever here. I want to find one where the digits don't add to 9. So let's keep going. 45, 54, 9 times 6 is 54, 9 times 7 is 63, 9 times 8 is 81, 9 times, whoops, I missed one here. 9 times 8 is 72, 9 times 9 is 81, 9 times 10 is 90, 9 times 11 would be 99. So if I look at all of these examples, 9, 18, 27, 36, 45, 54, 63, 72, 81, 90, I add up the digits and you can see that they're always 9. But let's look at the example 99. If I take 99, I add the sum of the digits. 9 plus 9 is 18. So this is not a the digits don't add to 9. And you can see I've made a little bit of an error here. 9 is the result. And we want to find one that doesn't equal 9. I shouldn't have said a multiple of 9. A multiple of 9 will be the sum of the digits in 9 will always be a multiple of 9. So in this example, I took the digits 18. I took the number 18, which is a multiple of 9. I took the digits, which are 1 and 8. I took the sum of those digits, which is 1 plus 8, and my result is 9. We want to find one that doesn't give us 9. Sorry, I had made a slight error there. So if I take the example 45, the digits are 4 and 5. The sum is 4 plus 5, which is 9. And if I look at any example here, 9, 1 plus 8 is 9, 2 plus 7 is 9, 3 plus 6 is 9, 4 plus 5 is 9, 5 plus 4 is 9, 6 plus 3 is 9, 7 plus 2 is 9, 8 plus 1 is 9, and 9 plus 0 is 9. But when I get to 99, which is 9 times 11, which is a multiple of 9, those digits don't add to 9. So this would be my counter example here because the digits don't add to 9.